Okay, so fundamental theorem of calculus, two parts. We did the second part first. You can do it either way. I found over the years, I used to do the first part and then the second part because that makes more sense. But I found that it's a little better understanding if you do the second part first and then do the first part second.
So that would make it.
Did I say that right?
The second part first.
Yeah, you did.
Yeah.
Good job.
And so your statement would be, well, why not just call the second part the first part and the first part the second part? Because everybody refers to the first part as the first part and the second part as the second part. Okay, so we'll get to other stuff later. Here's the important part. Meet somebody new today. Okay? Just saying. Don't get creepy about it. Just meet somebody new today. All right. We did this already. Here it is summarized for you. Once again, you take the derivative of an antiderivative from a constant to a variable. That's the important part. Of some function f of t dt, you get f of x. And notice, it doesn't matter what a is. That was one of the things that you should have gotten out of the lab yesterday, is that whether I start at 0 or 1 or 7 or a gabillion, it's still going to work out this way. I'm going to go because we did this already. This is the thing that we didn't talk about that pops up occasionally, and it's just something you need to file away in the back of your brain. Notice how I changed this problem. Okay, so instead of going from 7 to x, I'm going from 7 to x squared. So I put a different function in there instead of just x. T's become x's, but it's more elaborate than that because t's become x squareds. Does that make sense? You're not just changing t's to x's, you're changing t's to the function that's up on top of that Archimedes symbol. There is a small catch though, that 2x. You have to remember to chain on the derivative of that function up on top. Which is completely confusing, I understand, but hopefully will make more sense when we're done.
So you're putting x squared into t squared?
Correct.
Okay.
Okay, so for instance, when we did this, from 7 to x of the square root of t squared plus 1 dt, you would just get the square root of x squared plus 1. Right? Okay, just replace t's with x's. Now we have a different function here. So now x squared goes in for t. That's why this becomes x to the fourth. And you have to remember to chain on the derivative of this thing. So you could either remember that if the function is something other than x, you have to chain on the derivative, or just remember to chain on the derivative always. Because what's the derivative of x? 1. So there is a times 1 on the end there. Okay.
Wait, so why do you only do with x squared up to 7?
7 doesn't matter. That's just our starting point.
The a doesn't matter.
Okay.
Yeah. And you'll see why with the stuff we're going to do today. I know I'm asking a lot of you to be patient, but so for instance, what would going from 3? That's a 3. Okay, that's supposed to be a 3.
8.
Six.
Go with it.
What does that equal?
What are the t's?
2x.
Oh, it's a good question. That equals a train wreck. Hold on.
T squared.
A lot of t squared is going to start showing up soon. There we go. All right, what's that? Okay, so wherever you see a t, put in 2x minus 1. So this becomes 2x minus 1 quantity squared. Chain on the derivative of that, so you'd have a 2 at the end. Done. Don't need to multiply it out, don't need to do anything. This doesn't pop up very often, but it's still something you should understand. Question?
What does it mean when it's x squared instead of x? I know like the functions change, but like in terms of what you're doing mathematically, what does it change?
Can you wait?
Yeah.
Okay. Once we get a better understanding of what those numbers represent and how to solve the problem, you'll see.
Okay.
All right. It is a fairly minor point, but I would be remiss if I didn't explain it to you. Okay, so this is gonna get a little weird. I'm gonna take you through step by step the proof of the first part of the fundamental theorem of calculus. The application of the first part is pretty straightforward. The proof is a little scary. If you wanna write it down, great. If you just wanna be a mathematical sponge and absorb information, you can do that too. Okay, so we know that already, right? You've seen that 4 times already. I'm going to take 2 functions, capital F and capital G. They're both antiderivatives of some function f, okay, which is the one we already worked with over here. The only difference is the constants behind one. So we're going to define g of x as being f of x plus some constant. Remember we talked about the families of antiderivatives. You've got a whole bunch of different answers there. So we're going to say g is the antiderivative of this function f of t from a to x. F is also an antiderivative of that. It's just going to have a different c term on the end of it. And then we start doing some substitution to get where we need to go. Okay. Oh, by the way, what's g of a?
0.
Why?
Because it's a starting point.
Good. Yeah, going from 0 to 0 has no area under the curve, so this would be 0. That's important. It'll pop up in a second. So I get that. Okay, now that requires some explanation. I took this, instead of x's I put in a's, and we know that g of a is equal to 0. So I have g of a equals f of a plus c, but g of a is equal to 0, so I get that. Which means that c, that constant, is going to be the opposite of f of a. Question?
Yeah, so with the weird Archimedes symbol that we're naming it, does it matter if the numbers are to the right of it or on top and on bottom of it?
Doesn't matter.
It's
You'll see
different
it. You'll see it
notation.
both ways.
Okay.
A lot of it
But
has
they
to
mean
do
the
with
same
the
thing.
computer program that the person used to create it.
But they mean the same
They
thing.
mean the same.
Okay.
Question?
So if the antiderivative, or if g of a is 0, why is f of a not 0 also?
Because there's a constant involved.
But wouldn't it be 0 plus a constant?
That is true. Yeah.
Okay. Ooh.
I know. This is a big jump.
That heated up.
So instead of using A, I used a B. The same thing is true. I could put in G of puppies. G of puppies would equal F of puppies plus C. But I chose B because it's a little more mature. Yes, sir?
What did you do in the last one where you said it equals 0?
This one?
Yeah.
This step came from this step. I changed the x's to a's.
Okay.
That's where that came from. And we already talked about this step, g of a is 0. I put 0 in there for g of a.
Okay.
Okay, so double substitution.
Why would f of a be 0?
It's 0 plus a constant.
Okay.
Okay. Now, if I change it to b's or puppies or whatever, I get this statement. G of b is equal to f of b minus f of a. Because we know what c is now. Which gets us to, after all that stuff, that. And that is really important. That's the fundamental theorem of calculus. Which looks like gobbledygook right now, but
Need another piece of paper.
yeah, in the closet.
Was Newton just like bored one day and he's like, I'm just gonna write down a bunch of letters that
Yeah, watch this.
could make sense.
This will mess some people up. Leibniz, Schmeibniz. Didi.
So since they're both antiderivatives of the same function, what's like the explanation as to why you can plug in different values and still have the same pattern occur?
Think of your function as like x squared.
Okay.
So you got x squared and then x squared plus 3. I can plug 2 into both of those, and you'll get different numbers, but I can plug whatever, I can plug 2 in, and I would get 4 and 7. Okay, so it just allows you to plug whatever you want into it.
Okay.
And that's why they're a little bizarre there, because of the plus C. Okay, so this is the weird part. I wasn't sure if I wanted to show you this because it's very confusing, especially since the application of this theorem is ridiculously simple. As soon as this clicks, or it doesn't, it's gonna click like 4 times in a row. Oh, maybe not.
I have to write this one down.
Okay, so this is gonna allow us to take definite integrals now. Did we go back to the start? No, there we are, good, good, there we go. Okay. Still doesn't mean anything to you, right?
Not quite.
Well, there it is, tell me what it means. Oh, by the way, this is so important that I made it change colors. There we go, yeah. I like when it flashes better, but I was on a time crunch.
It went from
Sam.
important to
Why?
important though.
Why isn't f of a 0?
Because this is a general function. F of a being 0 was for the proof, but we don't need the proof anymore because we got to this.
Okay.
Okay. Casey?
It means that the area up to point B under the curve subtracted by the starting point is the area that you have.
Does that make sense?
Yeah.
Okay. How do I apply it?
So now.
So let's say, for instance, this, I don't know why I'm even trying this, but what the heck? I'll live on the edge. We'll use red. How do I use the fundamental theorem of calculus? That's a 2, by the way, up on top, sorry.
2x1.
Not quite. Okay, so what Casey is saying is I've got a function. In this particular case, I've got a function x, and I'm going from 2 to 1. From what we've done already, you could find this area, right? What shape is that? Trapezoid. Okay. What Casey's saying, however, is, well, you tell me, what did this mean?
That's the area under all of it, and then you subtract it by the starting point.
Okay. So this is that triangle.
And then you subtract the 1.
That is what?
That's the smaller triangle in there. Yeah. And you want to subtract that part out of the larger triangle.
Correct. Still doesn't help me solve the problem though, right? If I have a function lowercase f, what's capital F?
The antiderivative.
Good, so what's the antiderivative of x?
1/2 x squared.
1/2 x squared. This is all old stuff, we've done this before. So if I know what capital F is, what's capital F of b?
Whatever it is at 2.
X.
Whatever it is at 2.
Yeah.
So 1/2 2 squared minus, what's f of a? You good, Kevin?
Yeah.
Okay, thank you.
1/2
1/2 1 squared. 2 minus 1/2 3/2.
Cakewalk.
Done. That's an exact area. That's the same area you'd get if you calculate the area of that trapezoid. So why not just do the trapezoid? Well, you could.
Why did we count rectangles?
That's a good question. Why did we count well, it's the same analogy when we did derivatives, when we did all those difference quotients, the limit of the difference quotient.
Oh,
we did all
yeah.
those, and then all of a sudden I showed you the derivative of x squared is just 2x, and you got angry. It's kind of the
I
same
think
thing.
I'm a little more angry now just because the rectangles kind of were popped.
Yeah, because they're so far, they're so far away from the actual answer. Look at the rectangles.
Well, they don't have to be. Increase the number of rectangles.
You told us to
Takes
before.
forever.
I think I'm better at this
Okay.
now than I ever was at rectangles.
You're a rectangle master now?
No, I'm not a rectangle master.
He's
I'm
a
bad
he's
at
a definite
rectangles,
integral master.
but I'm okay at this now.
He's the fundamental theorem of
So you still struggle with rectangles, but you're okay with
Yeah.
integrals. I understand. All right, let's see this in action. The application is really simple. Take the antiderivative, plug in 3, plug in 0, subtract the 2, you're done. And that answer is the exact area. Because now the rules change. We have a nice pretty curve. I don't want to use rectangles, because as we've already discussed, many of you don't like the rectangles. And plus, that's not going to give me an exact answer. I'll have a really close answer. I could do like a sigma thing and throw that in there, but that's a headache. Who wants to do that? When I can just use the fundamental theorem of calculus. What's the antiderivative of x cubed?
1/4 x to the 4th.
Somebody who knows how to raise their hand. Dee
1/4 x to the 4th.
1/4 x to the 4th. Oh, notation, by the way. So, there's the antiderivative. Use a bracket or I usually just do a line. 3 and 0. Okay, so this shows that you know how to take the antiderivative of that. There's 3 plugged in, there's 0 plugged in, there's your final answer. If you FN int that, you'll get the same answer because they're both exact answers. Okay, anything tough about that? Obviously it's going to get tougher. How could we make it tougher?
Put in
Trig would be one option.
x squared instead of 3, or 3x squared or something.
Oh no, we're going to stay with numbers. We want to get numerical answers.
We're not
Yeah,
trying to-
we want to find areas under curves. I don't want to get too crazy.
Oh, way harder or antiderivatives. Nasty ones.
Multiple ones.
Multiple one?
There's just like a lot of them.
Oh, okay. I might have a couple of those.
Like, let's get like a.
Like that?
Just a couple. No.
No, that's okay.
I mean, yeah.
All right, good. You solved that one then. When you get an answer, check with your neighbor to see if he or she has the same answer. If not, fight about it.
Are you gonna put up the notes for tomorrow through Friday? No, like the slideshow, so that.
I don't know if there are. Well, there'll be a slideshow tomorrow, yeah. It's all one big slideshow, so I haven't posted it yet, but I will throw it up as soon as possible.
Okay. The top number, plug that into X.
I don't remember what the answer is. Yes, sir.
I left my calculator in this room yesterday.
Is it a black one?
Yeah.
Black TI-84?
Yeah, we saw it.
No, it was that one, it's like black and white.
It's, what's the predominant color? It's blue, right?
No, it's white.
Oh, I thought I could trick you. Yeah, I might have it in here.
Is this bid or is it dip?
For a price. And it's 2/3 times
Oh.
the three that you can.
Oh.
Calculator.
flying through the
Because, okay, so because you put the 3 out in front of that, then you have to do plus 1. This would be 2 bits, because it has to be there's like 2/3 times the 3 out in front. So it's just 2 extra than we had.
You can make us do these without a calculator.
Well, you will.
Oh, like these ones?
Yeah.
Oh, that's a little.
Dennis, no, we heard from you yesterday. Caleb, what's the antiderivative of x squared? I'm sorry, x to the, yeah, you.
Oh.
Why were you looking around? You know-
She's feeling too.
Oh, I'm sorry, I forgot, I didn't even, and I'm looking, and I'm like in a perfect line right, sorry.
Oh, what?
What's the antiderivative of x to the 1/2?
2/3 x to the 3/2.
Whoops. What next?
3 times 2/3 over to the 3/2 minus.
Yeah. I'm gonna do this though, I'm just gonna leave the 3 out in front and multiply that final numerical answer by 3. Okay, what do I do now?
You plug in 4 more.
Okay, so 4 to the 3/2. I don't want to calculate 4 to the 3rd power, but I can take the square root of 4 to be 2, and then 2 to the 3rd power is 8. So that's 16/3 minus, put in a 1, 2/3, 14/3 times 3, 14. Same. Question?
Do we have to use the notation for that, like when we're doing our work, or can we just?
It's a great question. What's expected is that you show a couple things. Number 1, show that you know how to take the antiderivative.
Right.
Number 2, show that you know what numbers you're going to plug in what order. But if you go from, if I'm grading this as an AP grader or as your calc teacher, and you go from here to here, the question I'm going to ask is, how the hell did that happen?
No, but like, do we have to have like the?
The little bar thing?
Yeah.
Yes.
Ugh. Okay.
Is that too much
I don't
work?
like it
Or
'cause, like, when you get-
you got a shoulder
I get-
problem,
I get
or
thrown-
you can turn your paper and go like this if you'd like, and then just turn it
No, I
back.
get thrown on like where to put it.
Oh, after the end of the
After
antiderivative,
the end of the.
before the equal sign.
Before the equal sign. Okay.
Okay.
Could you have multiplied the 3 out before you did everything? And
Sure.
just did it?
Yeah, you could. That's a great question. I'll change colors for that. You could have done, which I think is what you were saying, right? You bring a 3 in, so you could have done this. Yeah, that's good. That probably would have been easier because I wouldn't get 16/3 and 2/3. Okay, got it? It's not bad, right? Right. Okay, good. Let's see if we got it right. 14. Ooh, I'm afraid what's coming next.
Is it multiple functions?
No, should we do it anyways?
Let's just have trig.
Yeah, let's do some trig. There's some trig for you. End on a positive note.
There goes my 10.
I need trig to be an algebra. Yes.
Didn't trig like used to be its own class?
Hmm?
Cause like
Be
applying
its
for
own
college
class.
is like a separate
Yeah.
thing to be like if you're like, if you have to like do your grades and such, it like has like trigonometry as like its own math course that you took.
We just teach trigonometry.
It does?
Yeah.
Isn't
Like
that
it'll have
big?
like geometry, advanced algebra, and then there's supposed to be like trigonometry. And I didn't know where to put it, so I'm like, I've done it, but
Well,
like I.
because we incorporate trig into pre-calc. So a lot of places will teach it as pre-calc / trig. They won't incorporate the trig into the I mean, it's the same thing, you're still getting the same content, they just call it something different. You know, advanced algebra, algebra 2, same thing.
Isn't pre-calc just like algebra still?
It's the stuff that happens before calc.
Really?
But I mean, we didn't talk anything about like derivatives last year, so I mean, what really?
We could have.
Yeah, we could have.
Until like second semester was like new stuff.
What's the antiderivative of secant squared? Are you checking your note cards? Awesome. This is note card worthy. I love it. What is it?
Wait, I need to make the.
Tangent.
I need to make. So it says tan.
Wait, why don't you incorporate the plus C there?
Yeah,
Oh.
that was my question. We didn't do that on the last one though.
That's a great question. Where'd the plus C go?
Well, it's 'cause we're
It
finding
doesn't matter anymore because we're getting a
Yeah.
dominant area.
Why?
The lemon.
Okay. we banished.
Magic. It's magic.
It's magic.
It's like how the X goes to
That's
T.
T goes.
You have no idea, do you? Okay.
But I know it's going.
It is gone, yes.
Because it's
What we're calculating now is a numerical value, not a function. So we take an indefinite integral, we're getting a function. And you need a plus c because you've got a family of possible functions. This is a numerical value, area under the curve, number, no other possibility. Okay. All right, I'll ask anyways. What's the tangent of pi over 4? Oh, woo! I was worried about that. What's the tangent of 0?
0.
Okay.
See, this one isn't scary, but what about the ones that combine like sine and cosine? Those I don't like.
Well, remember, there's no, this is something that many of you forgot on the quiz. There's no quotient rule, product rule, or chain rule in integrals.
You get that quiz?
Oh, I know you're
Not yet. A couple people still need to take it.
J doggy dog.
Couple people still need to take it.
Oh, it's
Wait,
not me
there's
this
a
time.
quiz.
You should just
I'm
make
proud
them
of
take it
myself.
now.
I did.
You say no.
Yeah, let's just put John on the spot and watch him take
Wait, no,
it.
you're-
Yeah, that would be too intimidating.
John, the quiz last week, they did like 15.
Oh yeah, we just made it worse.
14 though.
No,
Time this period over. 42. Oh, plenty of time.
Wait, is that absolute value?
it's like
Why, mystery?
How do you want to go
Oh, I guarantee you're not gonna like this one.
We should just draw this one out. We should just draw this one out instead.
just don't forget your
Rectangle's this one.
Yeah,
and answer.
Okay.
I like that.
Wait, yeah, if it's absolute value, you can do the triangles and the rectangles.
Yeah.
And get an exact.
But you still got a curve.
X squared.
An absolute values?
Of
Oh
x
yeah,
squared.
it's quadratic. Ding, ding, ding.
I'd rather not.
I can't do it.
Anybody know how to take the integral of an absolute value? Me neither.
Next question.
So let's get sneaky.
It doesn't just go away.
Can we just make it go away?
Yeah, it's the C.
Kev,
It just vanishes.
just because we start integrals doesn't mean you pick up on a new buzz phrase. You can't just drop limits now and change it to it goes away. What's the area under the curve? It just goes away. Any idea what this looks like?
No, neither do you.
I do actually. Nice try though.
Three and it's like -1.
I'm sorry.
Like a W looking thing?
Like it, yeah, good. How would I get that? Can you graph x squared minus 2x minus 3?
Yeah.
Where's the vertex?
Negative b over 2a.
2.
Yeah.
1. 2.
2, 1?
No.
It would be 1 something.
Wait, 1 4.
Oh,
Like 1 negative 4.
Wow.
yeah, it is.
It's
Where's the
yeah.
vertex?
1 negative 4.
Is he right?
Yeah.
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 That's quick maths.
Now what? It's parabola. Does it open up or down?
Up.
Up. Good.
Plot points, plot points.
No. Well, we will, yeah. Find the zeros.
It's full.
Well, that's off a little bit.
Yeah, it's a little wonky.
That's not what you're saying.
No, it's got to open up.
If your X is 1,
I didn't space this out very carefully, but we get something that looks like that. That's horrible. That's the graph of x squared minus 2x minus 3. What's the absolute value do to it, Lexi? Be more specific. What do you mean flip it? Just flip the whole thing over?
So like that vertex thing is on like
Right,
the top.
you learn.
It has a maximum instead of.
So what's below the x-axis?
What's below the x-axis? Yeah.
Nothing.
Nothing.
No.
So,
Just goes away.
Yeah.
You're just inverting the hump.
Yeah,
there
like
you go.
that.
let's watch the mouth.
It's the hump inversion theorem.
See, so nothing below.
Well, that's fun. That's nowhere near to getting us close to the,
It's a semicircle.
Yeah, semicircle it up, semicircle it
it's not a semicircle.
What is it?
It goes away then.
Wait, Siri, I'm confused as to why. It's between the curve and the x-axis, and the other two just go, and the other two legs go on infinitely. So can't you assume it's a semicircle?
So we're looking for the area of this region,
Oh wait, yeah. 'cause
the area
it's
of this region,
Okay.
We got that one.
and we're stopping there.
Man's not hot.
Okay.
So it's a semicircle plus paradise.
That's not a semicircle. But I do know that I can break that into two integrals.
Is it the same thing for the sum of the integrals that applies for derivatives?
Say again?
Is it like the sum of integrals is the same as their individual sums or whatever it was? What was it for derivatives? Like the sum
The
of
derivative of a sum is the sum of the
Yeah,
derivatives?
is it the same thing for an integral?
Yeah, we've talked about that.
It goes away. Kelly taking it away.
Why?
There's two thumbs.
Because there's like two areas you have to find, but they're like not connected to each other. They're like separated, so you have to find the one from that and the one from that and add them together.
This part of the graph is just what we'd get if we did a normal function of x squared minus 2x minus 3. This is the reverse, I shouldn't say the reverse, the opposite of the normal function. So from -1 to 3, you would have the opposite of it. That's why I put that minus sign in there. Those are separate integrals. I succeeded in getting rid of the absolute value symbol, and so those are two things that I could just grind out. Question?
Is the reason you can't just take a straight one is because it's not continuous?
What's a straight one? I don't understand straight one.
Just like a full integral without having to stop it is because it's not continuous at 1.
It is
Or
continuous
or
at 1.
negative 1, negative 1.
It is continuous at -1.
Differentiable.
No, it's not differentiable, but we're taking integrals.
Doesn't it have to be differentiable for
They're
you
two
to-
different functions.
Yeah, but if you didn't split them up, wouldn't it have to be continuous and differentiable?
To take an integral?
Yeah, say that wasn't like a corner point at -1 and it was like a little above, it didn't touch the x-axis, you could just take the area under the whole thing without having to split it up, right? And the
If you knew how to take the antiderivative of an absolute value, which
Yeah.
we don't know, which is why we had to split it up.
Okay.
How can we make it worse?
We don't.
Make it a cubic.
Make it a cubic. Ooh, that would be, an absolute value of a cubic? That would be fun.
With trig too.
Yeah, so the value
Just
plus
sauce in
the
the trig,
trig.
x cubed plus.
Piecewise.
Get off the.
That would be too bad, because we would just split it, because then we then just have to plus whatever on the end.
We're really stupid.
What about piecewise?
Yeah.
Do you think
Oh.
this is
Yeah.
Dee Dee just asked a good question. What about a piecewise function?
No.
But you have to like faux draw some like dotted lines to like guesstimate where one ends and one begins. Because usually we do it where they're like nicely on like y values, but when they're not, or x values when they're not.
Okay. So if we do this, let's suppose my piecewise function
Yep.
Ramso.
Stop it, yeah.
Zip, zip. Sandy, go ahead and show us.
suppose that's my piecewise function,
We got a zombie.
and I want to find the area under the curve from A to B.
I think you have to split up.
Correct.
It's not
There's one. There's two. There's three. Now, what won't work is that if they don't, if the,
The other side be another one or no?
no, because this will take it all the way, we take this all the way back to A, so I should have done that.
Okay.
What won't work, however, is if there's a gap in between these two,
Yeah.
because then you have an infinite area because there's no function to take it down to the x-axis. Hey, there's the W looking thing. You have the slideshow sitting in front of you, don't you?
Yeah.
Oh my, what a hacker, what a hacker.
I was impressed that you actually knew that, you
Sorry.
little weasel. Actually, I think it's day 64.